Hi everyone, today is January 11th and we are doing the hard daily integral for today. So please try it out for yourself and then we'll start. So the way we're going to do this is we're going to use Feynman's technique or what's called the Leibniz integral rule. So we're going to define a parameter alpha and we're going to add this parameter right here. So x to the alpha minus 1 over x plus 1 times ln of x. And what we're going to do is we're going to differentiate this, and then we're going to come back and we'll be able to find our answer. So let's see how we're going to do this. So we'll first get I prime of alpha. And one more thing to notice before I move on, we have I of 0. So if x to the 0 is 1, so 1 minus 1 is 0, the integral of 0 is just 0. So I of 0 is 0. This is really important because we'll need a base condition. So after we differentiate, when we integrate, we can get a actual value. Or else a plus c could mean we can have any constant. So that would give us, that's not very helpful. So here, let's now actually differentiate this. So we'll take partial derivative with respect to alpha of this function. So the partial derivative, well, x to the alpha, that's going to be x to the alpha ln of x minus 1. The minus 1 will just become 0. And then we'll have x plus 1 over ln x, since that acts as a coefficient. Dx, the ln x and ln x cancel out, and we are left with the integral from 0 to 1 of x to the alpha over x plus 1 dx. So now we're going to use the infinite series representation of x plus 1 over x plus 1. So remember that from n equals 0 to infinity of x to the nth is equal to 1 over 1 minus x. So we can replace negative x, and this is just a geometric series. So this is just a geometric series, and we can use that to know that negative x to the nth is equal to 1 over 1 plus x. So we can rewrite this integral now as 0 to 1 of x to the alpha, and we'll use this geometric series now from n equals 0 to infinity of negative x to the nth dx. Now we'll swap the summation and the order of summation and integration as so. Now we'll have x to the nth times x to the alpha, so that's x to the alpha plus n dx. Now we can integrate this. So we'll have x to the alpha, so we'll have 1 over alpha plus n plus 1, x to the alpha plus n plus 1 from 0 to 1. And now we can put in our bounds. So it's at 1, we'll have x to the alpha, we'll have 1 to the alpha plus n plus 1. Well, 1 to any power is 1. So we'll have 1 over alpha plus n plus 1. And at 0, well, that's 0 to any power is just 0. So at that point, this whole thing would just cancel out, so we don't even need to consider that. So this is it. This is I prime of alpha. Okay, so now that we have I prime of alpha, we're going to integrate I prime of alpha to get I of alpha. So what is the integral of this now? Well, we can do it as such. 1 over alpha plus n plus 1 d alpha. Now this is just ln of alpha plus n plus 1 plus c. Since it's an indefinite integral, we need this plus c now. So now we have I of alpha. So I of alpha is equal to this sum. Now what we're going to do is we're going to know, using the fact that I of 0 is equal to 0, we're going to now get an actual formula for I of alpha without this constant. So we're going to figure out what the constant term is now. So I of 0 is equal to the sum, and since alpha is 0, this is ln of n plus 1. And here now we're just going to drop this absolute value since we know that this is positive. In this case, we can't really drop the absolute value considering that alpha could be negative. So now we can drop that absolute value of ln of n plus 1. This is equal, and we can't forget our plus c, is equal to 0. So we now have c is equal to negative, and from n equals 0 to infinity, negative 1 to the nth, ln of n plus 1. Okay, now what do we want to know? We want to know I of 1. X to the alpha, we want to know when alpha equals 1, what the value of this integral is. So we need to know I of 1. Okay, so let's write I of 1 now. I of 1 is the sum, negative 1 to the nth, ln of n plus 2, minus our c. Oops. Minus c, which is the sum from n equals 0 to infinity, negative 1 to the nth, ln of n plus 1. And as before, we can remove this absolute value. This is now positive. So now let's combine this into negative 1 to the nth, ln of n plus 2 over n plus 1. Now, okay, so we have a negative 1 to the nth here. This isn't very useful. We don't like this negative 1 to the nth, so let's remove it by considering when we have n equals 2k and n equals 2k plus 1. So when n equals 2k, we'll have negative 1 to the 2k power. So this is always positive. So the sum from n equals 0 to infinity, this is positive. ln, sorry, we're not using n anymore, we're using k. We have from k equals 0 of 2k plus 2 over 2k plus 1. Okay? Now for n equals 2k plus 1, this term is always negative. So we'll have ln of 2k plus 3 over 2k plus 2. Plus 2. Okay. So now we know that I of 1 is equal to the sum of these two series. The sum of these two series. And now let's again combine this to get the sum from k equals 0 to infinity of ln 2k plus 2 squared over 2k plus 3 times 2k plus 1. So now what we're going to do is we're going to convert this infinite series into an infinite product. So notice that ln of a plus ln of b is the same as ln of ab, right? When we're taking the summation, we're just saying that, let's say ln of ai, right, over like loads of i's is just the sum of ln of a1 plus ln of a2, right, on and on, right, let's say to infinity. So this is the same as ln of a1 times a2 times a3 and all the way on and on and on. So we can really write this as the product on I. Okay, we can write this as the product on I. So this is the same idea we're going to use here. We're going to rewrite this as a product. So this will become the product, the natural log of the product. So natural log of the product from k equals 0 to infinity of 2k plus 2 squared over 2k plus 3 times 2k plus 1. So this product is actually a very special product. This is 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5, on and on and on. This product is equal to pi over 2. This is called the Wallis product. And what this is basically an infinite series representation of pi over 2. So this is often used to find what pi is, right, using an infinite product representation. So our answer is actually just ln pi over 2. The Wallis product is often seen like this. This is often how you may encounter it, 2n squared. Well, you might see it like this, 2n over 2n minus 1 times 2n over 2n plus 1. So this is often how it may be written. It might be simplified, but this is equal to pi over 2. And this product now tells us that this answer is ln of pi over 2. This is equivalent to 0.45. So this is approximately 0.45. And so we have our answer.